In this video, we're going to talk about the Claisen condensation, and it's similar to the aldol. The main difference is instead of using aldehydes and ketones, now we're using esters. What we have are two molecules of ester reacting to give a beta ketoester. We're going to start like the aldol with the two molecules of ester being identical, and then later we'll look at crossed versions of the Claisen reaction. So here's a sample reaction where we have this ethyl ester and we're subjecting it to sodium ethoxide and dilute acid. I didn't write it in this case, but you could also include the corresponding alcohol here, which would be ethanol. It is important, as we've talked about before, that the base you use matches the ester OR group. That way you don't get any crossover products. So as written, this reaction is all you need to see that this is a Claisen condensation. Now, one thing that sometimes does throw people off is that I didn't write a 2 in front of the starting material. And you don't need to write a 2 because it's not like you're reacting, if you're doing a reaction that you have one molecule in a flask. That's impossible. So we have a whole solution with billions and billions of molecules. So you're going to have one that can react with another. But for clarity in this case, I am going to go ahead and put the 2 in. Just realize on like certain standardized exams, you don't have to see that 2 because there's many, many molecules around to react. This is a 2-step process where we add our base and then followed by an acidic workup step. And I'll start by just drawing the product for you, and then we'll go through the mechanism to see how it's formed. Here's the product, and this is called a beta ketoester because in relationship to the ester, we have a beta keto group. So the steps of this are pretty familiar. First is enolate formation. So we start with one molecule of ester. We'll draw in an alpha hydrogen. The base will take that proton. Giving us the enolate. Second part, like the aldol, is nucleophilic addition to the other ester. So here's our nucleophilic ester. I'm going to draw the second molecule in blue so we can keep track of it. That will add to the carbonyl carbon as a nucleophile. There's our new bond. And we get O minus, a methyl, and we have the O ethyl group. Now, here's where this really diverges from the aldol reaction in that in the aldol reaction, you're stuck at this point until you protonate the oxygen. But with this, we have the OET group, which can act as a leaving group. So now that comes down, you lose OET minus. 'minus. 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 So here's the part where people sometimes get thrown off in terms of the mechanism. We look to be done, and we did generate the product. It's the same product we have up above, but this reaction is not finished mechanistically, because as soon as you form the product and this base OET minus, we're going to get a fast acid-base reaction. We have these acidic alpha protons. Get a very fast acid-base reaction. So we reform another enolate. And get ethanol as a byproduct. And this acid-base reaction is the driving force. Because you end up with this conjugate base is more stable than the OET minus that you start with. So this explains why we need step 2, we need to add the dilute acid. To protonate this intermediate and leave us with our final product. So it is a bit unusual in that in the mechanism, we form the product, react the product away, and then have to reform the product. But that is the way this reaction does work. I want to walk you through the same Claisen reaction and its mechanism with the energetic consequences and plotting it on a reaction coordinate diagram. So here's the mechanism that we just went through, where you form your enolate, add it to the other ester, and so forth, and really pinpointing this step right here, which we said is the driving force. And explaining to you why we can't just stop at what is the product and say we're done. So if we start with our ester and our alkoxide, we have the first step of the reaction, which is an endothermic step to get the enolate intermediate. That will then add to the second molecule of ester to give this intermediate here. Right now I drew this intermediate a little bit lower than this one. The reason is, think about what you have. We have a negative charge here on the carbon versus the negative charge on the oxygen. That is a slight increase in stability, so it's a little bit lower. Next, we do the elimination step, where we form the carbonyl and lose OR minus. This step is a favored step from here, and this gives us our product, the beta ketoester. But if we still compare that to the starting material, where the energy is down here, the reaction is still endothermic up to this stage. So there's no favorable driving force up to that point. But then once you do the acid-base reaction, where this base that's formed reacts with the alpha proton, now you get this overall driving force step, which makes the reaction exothermic. So we're going down in energy. That makes the reaction favored. Then once we're to here, the reaction stops. It drives to this step, and then you can add the acid to protonate that and give you the final product. If you want this handout, you can find it on the website in the handouts folder.